Welcome to a hobby electronics tutorial designed to walk you through building a keypad combination lock circuit. I'm Dylan Z, and I'll be taking you step by step through the entire process of constructing this circuit on a breadboard, explaining the steps and components as we go, and hopefully providing a little entertainment along the way. Giving credit where it's due, this circuit was designed by Charles Platt and was published in Make Electronics, a book I highly recommend for any hobby electronics enthusiast. You can find this book from many online sources just by searching Make Electronics Learning by Discovery. It's simply the best book for beginner and intermediate electronics buffs out there. The keypad combination lock circuit we'll be working on today shows off features of push buttons, resistors, capacitors, integrated circuits, and more. It assumes you have a basic understanding of the fundamental components of electronics, but fear not. I will explain each component we use and the logic behind using it. So put on your hobby hat, grab your breadboard, and get ready to have some fun. As with any electronics project, safety is number one, so please make sure you follow the tutorial as it's presented. Though we will be working with very low voltages and currents, I highly recommend reading the safety tips on the two websites shown on your screen. Again, what we are working with poses no real risk aside from damaging components. The information there is very good to know. Now, before we get into the truly fun stuff, we need to talk about our power source. The integrated circuits we'll be working with demand a pretty strict voltage, right at 5 volts. Unfortunately, we can't just plug a 9-volt battery into the breadboard and go. We need to regulate it and bring the voltage down to 5 volts. If you already have a component that will do this, you're good to go, but if not, fortunately it is very easy to construct a 5-volt regulator. For the regulator, you'll need a 7805 5-volt regulator, a 0.33 microfarad electrolytic capacitor, a 0.1 microfarad ceramic capacitor, and 7 jumper wires. These components are readily available at online sources such as eBay, Amazon, digikey.com, just to name a few. My recommendation is to perform a search for electronics components and find a source that suits you. Here's the schematic for the regulator. Don't worry if you're not too familiar with building a circuit from a schematic. We're going to walk through constructing the 5-volt regulator right now. First, place the 7805 5-volt regulator at the top of your breadboard as you see here, with the bulky part of the component facing left. For this and all future instructions, I will indicate with a highlighted red dot which breadboard holes should be used when placing a component. When positive or negative polarity of a component is not easily seen on the screen, I will use the red highlighted dot for positive and a blue highlighted dot for negative. Next, place 3 jumper wires across the center of the breadboard as the photo shows. It's not absolutely necessary to use red and blue wires for positive and ground, but it is good practice and can help eliminate confusion as your circuit grows. Now insert the 0.33 microfarad capacitor into the breadboard holes as shown. Be sure to observe polarity with this component, as it is critical that the capacitor be positioned properly. On most electrolytic capacitors, you will see a lighter colored line running down the side indicating the negative lead. Again, the picture shows the red dot for positive and a blue dot for negative. Next, place the 0.1 microfarad capacitor in the highlighted holes. With ceramic capacitors, polarity is not a concern. Now insert the final 4 jumper wires as seen here. I have not indicated positive and negative because your breadboard's outside rails may not be configured as mine are. Suffice to say that the 2 wires originating on row 29 on this breadboard should lead to the negative rails on your breadboard, and the 2 wires originating on row 28 should lead to your positive rails. Finally, connect your 9-volt battery to the board as you see on the screen. The positive rails on either side of the breadboard now supply 5 volts, and the negative rails are your ground. You can test this as I have done here by setting your multimeter to indicate volts DC and connect its leads to your breadboard as shown. The readout on the multimeter should show a value very close to 5 volts. Congratulations! You've just completed building the 5-volt power supply for the combination lock circuit. I urge you to take a look at the 7805 voltage regulator datasheet at the website shown on your screen if you want further details on the specifications for this amazing component. Okay, now that we have the voltage regulator, we're ready to move on to the main event, the Keypad combination lock circuit. For this part of the project, you'll need a few more items. Hopefully you have them all at your disposal now, but if not, all are available, again, at a variety of online sources. Here's the list of things you will need. 3 100 ohm resistors, 2 1K ohm resistors, 4 10K ohm resistors, 1 100K ohm resistor, 4 standard LEDs, any color you wish, 1 10 microfarad electrolytic capacitor, 1 0.1 microfarad ceramic capacitor, 2 1N4001 diodes, this is a very common generic diode, 1 2N3904 NPN transistor, 1 HFD2 coil latching relay, 1 555 timer integrated circuit, 1 74HC04 hex inverter integrated circuit, 1 74HC08 2-input AND gate integrated circuit, 1 12-digit push-button keypad, or 12 tactile push buttons. I highly recommend using the keypad over the separate push buttons, however, and lots of jumper wire. You can buy the wire pre-stripped, or you can make your own. There are also several tools you'll want handy to aid in building this circuit. A pair of needle nose pliers, wire cutters, a multimeter, this is absolutely essential for troubleshooting and testing circuits, and of course a breadboard. This one will need to be a bit larger than the one on which I demonstrated the voltage regulator circuit. We'll need more room for all the components required here. The first component we'll be placing on the breadboard for the combination lock circuit is the 12-digit push-button keypad. This is also one of the more complex components and requires a bit of explanation. This particular keypad has one common pin connected to each button and 12 additional pins connected to each button separately, for a total of 13 pins. The common pin will be wired to a 5-volt rail, allowing current to pass through any particular button when it's pressed. The other 12 pins will be connected to various locations, depending on what we wish the button to do. The best way to explain the layout of the keypad is to simplify it a bit and pretend the keypad is made up of only 3 buttons, as you see on the screen. In this scenario, each button's left pin is wired to the 5-volt rail separately, indicated by the highlighted red dots, and each button's right pin is wired to an LED via a resistor. This calls for 6 total separate connections, 2 for each button. In this scenario, each button's left pin is wired to the other 2 buttons' left pins, and there is one common connection to the 5-volt rail. As in the previous scenario, each button's right pin is wired to an LED. This calls for only 4 separate connections, 1 for each button, and the common 5-volt connection. Both scenarios result in the corresponding LED being lit up when each button is pressed, because as the button is pressed and the internal connection is made, current is allowed to flow through the button and the LED lights up. The latter scenario, the one with the common 5-volt connection, simply allows for fewer total connections. This is made even more apparent as we take a look at the pinout diagram of the keypad. As you can see, each button's left pin is connected to the common pin at the top left of the keypad. Each button's right pin is connected to a unique output pin, as shown in the full diagram. It should be very clear now why this type of layout is preferred. We can simply wire the common pin to a 5-volt rail and wire the other output pins as we need to depending on the button's purpose. Now when each button is pressed, it will pass current from the 5-volt rail to its destination. Check your keypad's pinout diagram or datasheet to see how it's configured. It must have an output pin per button and a common pin. Unfortunately, a keypad with 7 pins, 1 for each row and 1 for each column, will not work in this circuit. Alternatively, as I mentioned before, you can use 12 separate tactile push buttons, wire the left pin of each button together and then to the 5-volt rail, Then wire the right pin of each button as the tutorial indicates. It's possible also that your keypad's pins aren't in the same order as the ones shown here. If that's the case, you'll simply need to modify the wiring of the breadboard to match your keypad's pin order. Okay, here we go. First, make sure your breadboard's power rails are wired so they can provide 5 volts and ground to the whole board, and then place the keypad as you see on the screen in the lower right-hand corner. If you're using push buttons, I would recommend placing them there as well. Let's get in a little closer to the keypad so you can see which holes I've placed the keypad in. It's not required, of course, that your keypad is placed exactly as mine, as long as you modify your wiring to accommodate for its position. Now we need to wire the 0, 8, 5, 2, 9, 6, and 3 buttons together as shown in the photo. The wiring here may seem a little jumbled, but it's actually very straightforward. I'm wiring 3 and 2 together and wiring them both to column 61 above the keypad. The same with 6, 5, and 0. 9 and 8 are also wired together and then to column 61. Later in the tutorial, we'll be using all of these buttons for the same purpose, and now all we have to do is run a wire from column 61 to achieve that goal. Finally, in this photo, you'll see that I've wired the pound or hash key with the red wire to somewhere off screen. That button will be used to reset the combination lock, but for now, let's just leave it dangling off the breadboard. The combination that I'll be using for this tutorial is 1, 4, 7. In that order, and I would recommend that you stick with that for the tutorial. But afterward, I urge you to get creative, change the combination, perhaps add digits to it, whatever you want to improve on or modify this design. Most of all, I want this to be a learning experience for you, something that you can take with you and apply to future projects. Now it's time to add our integrated circuits. Be careful with these as they are sensitive to static electricity and can be damaged with even a small static shock. Make sure you're grounded by touching something around you that's grounded first, especially if you're wearing socks. You can also use an anti-static wrist strap for extra protection against static buildup which could harm the components. I've been working with ICs for years and never had one blow due to static discharge. As long as you're careful, they will be fine. All integrated circuits have, or should have, a U-shaped notch on one end indicating the orientation of the chip. If yours do not have this notch, check the datasheet for your chip to see what the orientation indicator is. This must be known to be able to determine the pin numbers. In the example on your screen, the 7404 notch is highlighted. The pin numbering always proceeds counterclockwise from the top left, where the notch is oriented at the top of the chip. This particular integrated circuit, as you can see, has 14 pins. Let's go ahead and place the 7408 integrated circuit on the breadboard, as shown, with the notch facing left. As with all integrated circuits, it should be placed on the board so it's straddling a center line or ravine on a particular section of the breadboard. This is to ensure that each pin has its own set of connected holes. You wouldn't want 2 pins to be shorted together at all. I've highlighted the center line in blue for placement of this first IC, so there will be no confusion. And yes, you may have to slightly adjust the pins of the integrated circuit in order for it to fit snugly in the breadboard. Just be careful not to bend them too much. Now we want to insert the 7404 IC, as seen in the photo, again with the notch facing left. Right now, we're just placing the chips. I will explain their functions throughout the tutorial. Lastly, for the integrated circuits, let's place the 555 timer. This is a particularly famous IC that I'll be discussing in short order. I'll go ahead and zoom in to show just these 3 ICs on the breadboard so you can double check and make sure they've been placed properly. Next, we want to insert the latching relay in the upper right hand portion of the breadboard. This is a double pole, double throw relay switch and will have, if you've got the same relay I've indicated, 5 pins on each side. 2 of the pins will be close together and the other 3 spread evenly across the rest of the relay. The 2 pins that are close to each other will be placed on the left side, as indicated in the photo. I will go over the relay in further detail in the tutorial. Moving down the list, next we will place the LEDs as shown on your screen. I have indicated the positive and negative leads of the LEDs, as it may not be entirely clear from the photo. One thing to note about LEDs regarding polarity: you never want to apply positive voltage to the negative pin and vice versa. This will absolutely destroy the LED. There is no forgiveness factor here at all. So it's crucial to be able to identify the polarity of the leads. Most LEDs' positive lead wires are longer than the negative lead wires, assuming they haven't been cut. Another way to determine negative from positive lead is a small, flattened area on the bulb itself, as seen on screen. This flat area corresponds to the negative side of the LED. The lead on that side will be negative. You will likely be able to determine polarity of your LEDs using one of these methods, but if not, check the data sheet for the LEDs to make that determination. It's time to start wiring power to these components. We'll start with the keypad. Place a jumper wire as you see on screen, the brown wire, from a 5-volt rail to a hole in the same bus occupied by the leftmost pin of the keypad. Remember, this is the common pin. This will supply 5 volts to all of the buttons. Now, wire the second pin from the left on the keypad to pin 14 of the 7408 IC as shown in the photo. Recall that the second pin on the keypad corresponds to the asterisk or star button. This button will be used to supply power to all the integrated circuits on the board. Again, your keypad's pin ordering may be different, so make sure you're wiring from the appropriate pins. Now run a wire from pin 14 of the 7408 to pin 14 of the 7404. Then from pin 14 of the 7404 to pin 8 of the 555 timer IC. You may have guessed that these pins on the ICs are the voltage in pins and supply power to the chips. Now we will supply ground to all the necessary pins on the ICs. Go ahead and place the wires as you see in the photo. All of these wires are supplying ground to the pins on the ICs that require ground, except for the top brown wire. It is supplying power to the reset pin of the 555 timer, but we'll get into that later. Please double check your wiring before moving on. Next, we will place our first resistor. Wire one of your 1K ohm resistors from pin 8 of the 555 timer to the bus occupied by the positive lead of the LED as shown in the photo. This is simply supplying power to the LED originating from the asterisk or star button on the keypad. We want this connection so that when we press our power key, it is indicated by this LED lighting up. The reason we used a resistor instead of a wire is to ensure excess voltage is not applied to the LED, which could damage it. Now, assuming you've connected the 5-volt regulator to the positive and negative rails of your breadboard, when you press the power key, again the asterisk or star button on the keypad, the rightmost LED of the 3 on the left side of the board should light up, indicating that the ICs are all receiving power. This is a good thing. You can see just how much voltage is being used by the 7408 chip, for example, by placing your multimeter in its volts DC setting, connecting its leads as shown on the screen, and pressing the power key. Similarly, you could test the other two ICs just by moving the positive lead of the multimeter to the power pin of the other two ICs. It needs to be said at this point, and it should be clear from the wiring of the circuit we've completed thus far, that in order for power to flow to the components, the star key must be pressed. This means that while entering the 1, 4, 7 combination, the star key must not be released, otherwise the chips will lose power and the combination must be restarted. Think of this as added security and control for the combination lock. Because we are now going more deeply into the logic of this circuit, we need to take a few minutes to talk about the two logic chips we are using, the 7404 hex inverter and the 7408 quad 2-input AND gate. Let's start with the 7404 hex inverter. This chip is designed to take up to 6 separate logic inputs, hence the term hex, invert their values, and output the result. You can see from the diagram on screen the layout of the input-output pins. The logic symbol displayed next to each pair of pins is the accepted symbol for NOT or invert. They both mean the same thing. Let's focus on the first pair for clarity. Say, for example, I feed a 5-volt signal, or high signal, into one of the inputs. The corresponding output will be 0 volts, or low. From this point on, I will refer to the 5-volt and 0-volt signals as high and low, respectively. Conversely, if I feed a low signal into input 1, a high signal results from output 1. This can be done with any number of the 6 available input-output pairs simultaneously. This is very handy when we wish to supply a high or low signal to any component, and we would like that value to change under certain conditions. Say we wanted to feed a constant high signal to a second logic chip, but we wished for that signal to go low if a button were pressed. We could feed input number 1 of the 7404 the output from the button, which by default would be low. The signal from output number 1, or pin 2 of the 7404, would then be high, the desired signal we wish to send to our second logic chip. Should the button be pressed at any time, input number 1 of the 7404 would suddenly go high, causing its output to invert, or go low. The low signal is now sent to the second logic chip. As you can see, the function of this chip is quite simple, but its applications are boundless. Now let's look at the 7408 quad 2 input AND gate chip. This integrated circuit is made up of 4 sets of 2 input AND gates. The diagram on screen shows the layout of the input-output pins. The logic symbol displayed next to each triplet of pins is the accepted symbol for the AND operation. We'll focus on just one set to better explain. The first 2 pins of the set are the inputs, shown in red, and the third pin is the output, shown in blue. The output is low at all times, except when both inputs are high. Then, and only then, will the output be high. Say, for example, we want a high signal to be sent to a second logic chip only when 2 buttons are being pressed at the same time. In this case, we would feed the output of one button into input number 1 of the 7408, and the output of the other button into input number 2. If neither of the buttons is being pressed, the output is low, because neither of the inputs are high. If only one button is pressed, the output is still low, because only one input is high. Only when both buttons are being pressed at the same time will the output be high. These 2 logic chips used together will allow us to realize the combination lock circuit. If we think of the sets of inputs and outputs of the 7408 as performing some action when a condition is met, say a button being pressed, we can start to see how this circuit will work. It starts getting more clear, too, when we imagine that the input-output sets of the 7408 can be unlocked in sequence as certain buttons are pressed, and the final output can be used to drive a timer or a relay or both. This simple diagram animation will demonstrate essentially how the combination lock circuit will work. There is a bit more to it than this, but we will fill in the gaps as we go. First, the 3 keys, 1, 4, and 7, are shown wired into the 7408 at pins 1, 4, and 10. Initially, of course, they are all sending a low signal to the chip. As well, we can see that the final output of the 7408 at pin 8 is also low, as we would expect. Here we see that all the other pins are low to begin with as well. Nothing is going on with this circuit at all. Now we see pin 2, which is the second input of the first input-output set of the 7408, go high. This will be achieved via the 7404 inverter. This is the true starting state of the circuit. Now we see key number 1 on the keypad pressed and the results of that action. Pin 3 goes high, causing pin 5 to go high as well. Key number 4 is then pressed, causing pin 6 to go high, which in turn brings pin 9 high. Finally, key number 7 is pressed, causing pin number 8 to go high. What pin number 8 does we will discuss further along in the tutorial. Go back and watch this part again if you need to make sure it's clear. We need the first input-output set of the 7408, we'll call it the number 1 set after the first digit of our combination lock, to have one input already high, so that when the first button in the 147 sequence is pressed, it will cause the second input to go high, thus satisfying the condition and forcing the output high. So the first order of business is to ensure that one input of the number 1 set is high. This can be accomplished by using the first input-output pair on the 7404 inverter. Remember what we need to do to get a high signal from the input-output pair? That's right, we make sure that the input is low. This is done by wiring a 10K ohm resistor from the input pin, in this case pin 1, to ground. This is called pulling the pin low, and the resistor in this case is called a pull-down resistor. Go ahead and wire that now, as shown on the screen. Next, wire the output from the 7404 input-output pair, pin 2, to the second input of our number 1 set on the 7408, pin number 2 of the 7408, as shown on the screen. Now, when the ICs are powered up, by default the 7404 chip's pin 1 will be low, its pin 2 will be high, and the second input of the number 1 set on the 7408, pin 2, will be high. You can see this in action with the multimeter as I am monitoring the voltage on pin 2 of the 7408 while the power button, the asterisk key, is being pressed. So now one of the inputs on our 7408's number 1 set is high. What do we do with the other one? You guessed it, we wire the output of the number 1 key on the keypad to that pin. Before we do that, however, we want to pull that input low and have it stay that way until pressing the button forces it high. Go ahead and wire a 10K ohm resistor from pin number 1 on the 7408 to ground, and wire key number 1 on the keypad to that same pin, as shown on the screen. What do you think happens now when we press the number 1 key on the keypad? Well, that forces pin number 1 of the 7408 to go high. Now the condition of the number 1 set is met, and that set's output pin, pin number 3 of the 7408, goes high. This is excellent. We can now use that high signal to feed one input of the second set on the 7408. We'll call it the number 4 set, after the second digit in our combination lock. Go ahead and wire that now, as shown on the screen. But you may have guessed there's a problem. As soon as we release key number 1 to start to press key number 4, what happens? The first input of our number 1 set on the 7408 goes low. This causes the output of the number 1 set to go low because its condition is no longer met. This is a problem because the first input of our number 4 set is no longer high, and now, even if we press the number 4 key, we cannot meet the condition and unlock the second set. We can resolve this issue with the use of a diode. Think of the 1N4001 diode as a valve. It allows electricity to flow one way but not the other. This is exactly what we need to lock the number 1 set on even after the number 1 key has been released. We simply wire the positive end of the diode to the output pin, pin number 3 of the number 1 set, and the negative end back to the first input of the number 1 set, pin number 1. Go ahead and wire that now, making sure to observe polarity when placing the diode. The negative lead of the diode is marked with a small gray band. Taking a look back at the diagram flow, you can see how this diode will fit into the circuit. I've highlighted the diode in purple so you can easily spot it. The positive lead connects to pin 3, and the negative lead to pin 1. You can see from the multimeter readings I have taken that, while holding down the power key of course, the output, pin number 3 of the number 1 set, goes high when key number 1 is pressed, and stays high even after key number 1 is released. Now we can proceed to wire the number 4 input-output set on the 7408 pretty much the same way. Wire the pull-down 10K ohm resistor, as shown on screen, from pin number 4 to ground. Remember, pin number 4 is the first input of the number 4 set. Now wire the output of key number 4 on the keypad to that same input as shown. Again, the output of this set must be fed into the second input of the next input-output set on the 7408. We'll call it the number 7 set. Wire that as displayed. When that's done, wire a diode back from pin 6 to pin 4 to lock the second set on, as shown on your screen. Check pin 6 now with the multimeter as I have done. You'll see that pin 6, the output of the number 4 set, stays high after the 1 and 4 keys have been pressed and released in sequence. For the number 7 set on the 7408, we will follow almost the same process. Proceed with wiring the 10K ohm resistor to the first input, pin number 9, as shown on screen, followed by wiring the keypad pin corresponding to the number 7 key to that same input pin. Now, if you were to test pin 8, the output of the number 7 set, with the multimeter, you would see that it goes high after keys 1, 4, and 7 have been pressed in sequence, but goes back low after the number 7 key is released. This is because we're not feeding the output back into the first input via a diode, and this time we don't need to, because all we're concerned about is getting a brief high signal from the output at pin number 8. Now we need to wire pin number 8 to the second input-output pair on the 7404 inverter, pin number 3, as you see on the screen. If you'll recall, an input on the 7404 is inverted and fed out of the corresponding output pin, in this case pin number 4. So when the final output from the 7408 is fed into pin 3 of the inverter, the output from pin 4 will go from high to low. This low signal will be used to trigger a timed high output signal on the 555 timer. Before we move on to that, let's take a moment or two to look more closely at the 555. The 555 timer is a very complex integrated circuit that has been around for a long time. It is the most widely used integrated circuit in use still today. It has countless applications, most of which involve timing, pulse generation, and oscillation. It has 3 operating modes: monostable, astable, and bistable. The one we are concerned with for this circuit is the monostable mode. We will be producing a timed positive pulse that will activate a connection in the latched relay by utilizing a transistor as a switch. I strongly urge you to read up on and experiment with the 555 timer, as it is simply a fascinating component. You can learn more about the 555 at the website shown on your screen. I will also be working more with the 555 in future tutorials. Due to its complexity, I won't be going into a great deal of detail about the 555 here, but here's what we need to know for this application. When wired in monostable mode, as you see here, a positive pulse is produced at pin 3, the output pin, when pin 2, the trigger pin, goes low. The duration of the pulse is determined by the size of the resistor at pin 7 and the capacitor at pin 6. In this circuit, the pulse duration is about 1.1 seconds. You can modify the duration of the pulse by using different resistor and capacitor sizes on pins 7 and 6. The website on your screen has a calculator that will show you exact durations of the pulse when you enter the resistor capacitor sizes. Let's go ahead and wire up the 555 timer. First, we need to connect pins 6 and 7, as shown on your screen. Then connect the 100K ohm resistor from pin 7 to pin 8, followed by the 10 microfarad capacitor from pin 6 to ground. Make sure to observe correct polarity here. Next, wire the 0.1 microfarad capacitor from pin 5 to ground. This is simply ensuring that this pin, which is not used in monostable mode, doesn't cause any kind of interference with the other pins. Finally, wire the output of the second input-output pair on the 7404 inverter to the 555's trigger pin, pin 2, as shown. Remember that the output of the inverter at pin 4 is forced low when key 7 is pressed, which will then trigger the pulsed output of the 555 timer. The output of the 555 at pin 3 can then be used to switch the latched relay, forming a connection that will light the final target LED in the upper right-hand corner of the breadboard. This connection can be used for any practical purpose where a connection is required, and the beauty of it is that once the connection is made by the pulsing of the 555 timer, the relay will keep the connection in place even after the power key is released. Let's take a quick peek at the latched relay for a moment. If you're familiar with double pole, double throw relays, you already know how this relay works. If not, don't worry, it's fairly simple. There are two possible sets of two connections that can be made with the relay. The first connect these two sets of pins, shown on the screen, and the second connect these two sets. These two connections can be switched back and forth by applying power to the two sets of power pins. Here's the first set of power pins, and here's the second. The on-screen diagram now shows which connection is made as each set of power pins is activated. Here are the results of the first set of power pins being activated, and here are the results of the second set. Remember the pound key on the keypad that we wired the long red wire from? That wire will energize this set of power pins and cause these two connections. Go ahead and wire the green ground wire as shown on your screen, followed by placing the red wire from the pound key as shown. Now, pressing the pound key will connect these two sets of pins. This acts to reset the combination lock. Run the white wire as shown on your screen, followed by the 100 ohm resistor, to the second LED on the left side of the breadboard. This simply gives us a visual indicator when the pound key is pressed, the corresponding relay connection is made, and the combination lock is reset. Now run a wire from the 5-volt rail to the other relay power pin, as shown. This power pin set is the one that will be activated by the 555 timer. Unfortunately, there is not enough power from the output of the 555 to throw the relay switch, so we'll need to use a transistor, the 2N3904, to connect the relay's power pin to ground when the 555 is triggered. The transistor looks like this up close. It has a collector and emitter pins that are connected together when there is enough current passing through the base pin. The pulsing of the 555 timer will be connected to the base pin, supplying just enough current to switch the transistor on, connecting the collector and emitter pins. Go ahead and place the transistor as shown on the screen. I have labeled the 3 pins so it will be very clear where they should go. Now wire the 1K ohm resistor as shown on screen. Next, connect the 555's output pin to the 1K ohm resistor as shown. So we can visually verify the results, go ahead and place the blue wire as shown on the screen, followed by the black wire, then the final 100 ohm resistor to the LED. Those 3 wirings have connected the LED to power with the resistor and to ground via one of the resulting relay connections. At this point, when the 555's output is pulsed, it will pass through the 1K ohm resistor through the base of the transistor. As I mentioned before, there is just enough current now passing through the base of the transistor to allow the larger current to pass from the collector to the emitter. This is essentially using the transistor as a switch. It receives the small current from the 555 and turns on the transistor, allowing the larger current from the 5-volt rail to pass through the relay and then through the transistor to ground. The relay then switches to the opposite connections, lighting up the target LED. Let's make the final connections as shown on screen. First, connect the 555's output to the red LED via the 100 ohm resistor. This will give us visual verification that the 555 has pulsed. The LED will stay lit for the duration of the pulse, as long as the power key is held down. Remember the very first wiring we did at the keypad, where we connected all of the unused keys together and bundled them at column 61? We need to run a wire from that column, as shown, to input 1 of the 7404. What does this do? Think for a moment what would happen if pin number 1 of the 7404 went high while someone was attempting to enter the combination. It would immediately cause pin 2 to go low, because it's an inverter, which would then cause the number 1 set on the 7408 to go low, as well as any additional outputs on the 7408 that had already been locked high, including the final output, pin number 8, nullifying any entry that had been made up to that point. Essentially, it results in stopping the unlocking sequence in its tracks should any wrong key be entered at any point in the process. Pretty slick, huh? Your circuit is now complete and ready to be tested. For your reference, here is the completed circuit on the breadboard. And here is the schematic. Now hold down the power key and press the 1, 4, and 7 keys sequentially. As long as your wiring is good, your results should match those you are seeing on screen. The combination lock is complete. As I mentioned before, the relay connection made by completing the combination key sequence could be anything that requires a connection, not just to light up an LED. Use your imagination and think of some other applications for this circuit. Feel free to modify and tinker around and come up with new and exciting things to do with the knowledge you've gained about the various components here. The logic chips alone can be used to create all kinds of interesting circuits, from games to LED dice to full-fledged calculators or even computers. The possibilities are endless. I hope you enjoyed this keypad combination lock circuit tutorial, and I hope you use this to continue along your path in hobby electronics. Subscribe to my channel if you haven't already, and check back soon for more electronics tutorials. I'm Dylan Z. It's been a pleasure taking you through this journey, and I wish you all the best. So long for now.